Welcome back, students. Let's look at the Grignard reaction. The Grignard reaction involves a reagent called the Grignard reagent. The Grignard reagent is not one that you can purchase. You need to make it in lab. And it's one of our new ways that we're going to see that we can add carbon to a compound. To create the Grignard reagent, what you do is you start with an alkyl halide and you add solid magnesium. And when I say solid magnesium, imagine that you're in lab and you have a liquid alkyl halide and you add shavings of magnesium to the flask. Then you also include anhydrous ether. Ether is the solvent and anhydrous means without water. And what happens during the course of this reaction to form the Grignard reagent is the magnesium essentially inserts itself before the bromine. This creates a superpolar bond, but polar in an unusual direction. We're used to the carbon being the partial positive, but in this case, with electronegativity values, the magnesium is what bears the positive charge. So sometimes people will draw the Grignard reagent as a carbanion instead of drawing it like we see here. You can draw the counter ions here too if you'd like. So this Grignard reagent has to be created, but there's some stipulations. Once you create the Grignard, your goal is to have the Grignard behave like a nucleophile and attack the carbon of a carbonyl. The problem is that if there is an acidic proton that is present, the Grignard is going to behave as a base before it behaves as a nucleophile. This is part of the reason why you need to carry out your reaction in anhydrous ether, which means without water, is because your Grignard is actually a super strong base. It will just react with any acidic proton before it's going to behave as a nucleophile. So you just spent a whole lot of time and effort to create benzene and magnesium with one bromine and then a hydroxide running around. The other thing that you need to be aware of is that Grignard reagents can't be produced if there's an acidic proton on your compound. So there's two stipulations. One is that if you've made the Grignard and you allow that Grignard to react and there's an acidic proton present, that Grignard is going to behave as a base and pull off that proton well before it's going to behave as a nucleophile. The second thing is that Grignard reagents can't even be formed if there is an acidic proton on the molecule. And we're going to look at that idea in another video. Let's look at the mechanism for the Grignard reagent. For the mechanism for your Grignard reagent, remember that this bond between magnesium and carbon is very polar, pointing in the direction of the carbon. What will occur is that those electrons in the bond are what are behaving as your nucleophile, and they're going to attack the carbon of the carbonyl. When this occurs, we open this up to the tetrahedral intermediate that we saw in an earlier video. And you're going to notice that my Grignard reagent that I'm using in almost all the examples is going to be phenylmagnesium bromide because it's just really easy to see that that group added, right? If I were to do methyl magnesium bromide, it's harder for your brain to register, but it's totally a thing that can be done. It's just, I want you to visually see what's adding. Now we get to this thing which we called the tetrahedral intermediate. We ask ourselves, is there a good leaving group? The answer is no. Carbon things aren't good leaving groups. So what we do is we go through a protonation step. You might see some people write water here, other people might write acid. In real life, what I would do is I would add water dropwise first until the reaction stopped looking scary. And then I would add a little bit of acid to make sure that that O- was actually protonated. So we'll go through and have a proton transfer step. And now we have an alcohol and we've added a benzene ring. So what happens if you start with a ketone, you get one addition of Grignard and you end with an alcohol. The same thing is going to happen with an aldehyde, but it's going to be different if you have an ester. So let's look at that next. If you have an ester, what you need is an excess of Grignard. Why? Because the Grignard is going to react twice. Just like how we saw lithium aluminum hydride reacting twice with an ester. So the same type of thing is going to happen at the beginning. Your pair of electrons between the magnesium and the carbon are going to behave as your nucleophile, and they're going to attack the carbon of the carbonyl. That's going to force this bond to break and have those electrons go up onto that oxygen, which creates the tetrahedral intermediate. Now that I have the tetrahedral intermediate, I need to ask myself, do I have a good leaving group? In these reactions, OR groups are good leaving groups. So if I had an OET, an O-ethyl, an O-methyl, an O-propyl, an O-isopropyl, OR anything is going to be a good leaving group because this pair of electrons, or any of the pairs on the oxygen, doesn't actually matter, is going to collapse and reform the C double bond O. And when it does that, we need to push something else out. And that is going to be the OET. Now, what we end up with is the reformation of the C double bond O, which remember is called a carbonyl, and the addition of that benzene ring. But remember, Grignard is reactive to ketones. So because I have extra Grignard, this reaction is going to happen again. So with my excess Grignard, we're going to see another addition happen, which is going to follow the same type of mechanism where the Grignard attacks the carbon of the carbonyl, which is C double bond O. It opens up to form the tetrahedral intermediate. I see a second addition of a benzene ring. Now I'm at the tetrahedral intermediate. I ask myself, does this have a good leaving group? No, because it's all carbon groups. Thus, I must protonate. Again, some people are going to write acid here. Some people are going to write water. In real life, it's probably safest to do water and then acid so that you don't get anything too vigorous, because the Grignard's always going to be your excess reagent, and that means you should have extra at the end of the reaction. And if you just added acid to Grignard, that could be really scary. And now we end up with 2 benzene rings being added and an alcohol at the end. Again, you can change the identity of your Grignard reagent. It doesn't have to be phenyl magnesium bromide. It can be any carbon group where I'm highlighting in blue. It just is really visually clear when I use a benzene ring that 2 benzenes are adding during the course of this reaction. Here are some examples where I show you that you don't have to choose the Grignard reagent that I've been choosing. I want you to go ahead, take a moment, predict the products for these, and then come back and we can compare answers. All right, let's compare. So for this first one, what I did was I redrew my carbon structure, and where the C double bond O was is where I'm now going to have an OH. Because this is an aldehyde, my Grignard only adds once. And here is the carbon structure of my Grignard, and here is where I see that addition happen. For the next one, I have a ketone, so I redrew my carbon structure, and where my C double bond O was, I now have an OH. Remember that whatever my carbon part is for my Grignard is what is also attaching to the carbon where the OH is. Because this bottom one has an OR group here, that's an ester, which is a good leaving group, which means I'm getting 2 additions of the Grignard. pH-MgBr, that's phenylmagnesium bromide. That is just the abbreviation for this Grignard reagent that we've been drawing on the previous pages. So again, I redraw my carbon structure. So there's my carbon structure. I find my carbon where the C double bond O was. That's where I put in my OH, and because I have an ester, I see 2 additions of the Grignard, so I've put in 2 phenyl groups there. So here is my Grignard carbon structure, and I'm adding not once, but twice. I think it's really important to know the mechanism for the Grignard, but also to be able to simplify it so that you can go through and answer questions without having to draw the mechanism every single time. Let's wrap up. In this video, we looked at the Grignard reagent. We said that the Grignard reagent cannot be created in the presence of an acidic proton, because what we want to have happen is once the Grignard reagent forms, it needs to attack the C double bond O, so it needs to attack that carbon. And we produce an alcohol as a product, and we're also adding carbon to our chain. So if you followed my advice in an earlier video where I said to make a list of all the reactions that are in their own category, one of those categories I said was categorize all the reactions that you could use to add carbon or remove carbon. And now we've just added a new reaction where we can add carbon. So add Grignard to that list. Thanks so much for your attention. This is Ketone signing out.